We'll be discussing direct assembly of the stiffness matrix K and the load vector P. This will be applied to continuous beams, but the method is rather general and can apply to structures of all types. This will be a method of assembling the stiffness matrix and load vector much quicker and in a less confusing manner than working through the equilibrium equations explicitly. So let's see how this is done. We'll be using our previous example. This is a two-span continuous beam with the uniform load over the whole structure. The degrees of freedom are rotations at all of the nodes, and we're showing here the forces on the members and the nodes due to a displacement at degree of freedom 1, a displacement at degree of freedom 2, and a displacement at degree of freedom 3. We're showing as well the forces on the members and the nodes due to the applied load with all of the nodes held in their positions. In all of these diagrams, we've omitted the shears because there are no translational degrees of freedom. Recall the definitions of the stiffness matrix and load vector. The stiffness matrix Kij is the force at the ith degree of freedom due to a unit displacement at the jth degree of freedom. The load vector Pi is the applied force at the ith degree of freedom. We previously defined the sign convention for these quantities. The stiffness matrix K is positive opposite to the ith degree of freedom. The load vector P is positive in the direction of the ith degree of freedom. Now this sign convention has physical sense. The elements of the stiffness matrix resist an applied load, and that is why they're positive opposite to the degree of freedom. The loads tend to move the node in the direction of the degree of freedom. Let's work now with the definition of the stiffness matrix and keeping in mind the sign convention. And we'll go degree of freedom by degree of freedom and see how we can determine each of the elements of the stiffness matrix from what we have on the screen already. Let's start on the diagram for displacement at degree of freedom 1, and we'll look at degree of freedom 1. I'm showing here the orientation of the degree of freedom. We can see that on that node there is a moment of m1. That moment is opposite to the degree of freedom, so it's positive. And so K11, the force at the ith degree of freedom, at the first degree of freedom, due to the unit displacement at the first degree of freedom, is equal to m1. Now we'll do K21, the force at degree of freedom 2, still due to a unit displacement at degree of freedom 1. We're showing the direction of the degree of freedom. The moment is m2. The direction is opposite to the degree of freedom, so it's positive. So K21 is equal to m2. For the next degree of freedom, K31 is the force at the third degree of freedom due to a unit displacement at the first degree of freedom. There's no moment there, so the stiffness term is 0. We'll move on to the next diagram, displacement at degree of freedom 2. Looking at node 1, it's the term K12, the force at the first degree of freedom due to a unit displacement at the second degree of freedom. The total force on that node is a moment of m2. The direction is opposite to the degree of freedom, so the sign is positive. K22 is the force at the second degree of freedom due to a unit displacement at the second degree of freedom. The total value of the force is a moment of 2m1. The direction is opposite to the degree of freedom, and so the sign is positive. For K32, that's the force at the third degree of freedom due to a unit displacement at the second degree of freedom. The total force on that node is a moment of m2. The direction is opposite to the degree of freedom, so the sign is positive. Moving on to the displacement at the next degree of freedom. The term K13 is the force at the first degree of freedom due to a unit displacement at the third degree of freedom. There's no net force on that node, so K13 is 0. K23 is the force at the second degree of freedom due to a unit displacement at the third degree of freedom. The net force on that node is m2. It's opposite to the degree of freedom, so the sign is positive. Moving on to K33, that's the force at the third degree of freedom due to a unit displacement at the third degree of freedom. The total force is a moment of m1. The direction is opposite to the degree of freedom, so the sign is positive. Now we'll work with the definition of the load vector. P sub I is the applied force at the ith degree of freedom, and it's positive in the direction of the ith degree of freedom. So looking at the left-hand node, P1 is the force at the first degree of freedom. The value is a moment m3. The direction is opposite to the applied load, but the sign convention is switched. So in this case, if it's opposite to the direction of the applied load, it's negative. That means that the load tends to rotate the node opposite to the direction of the degree of freedom. Moving on to P2, that's the applied force at the second degree of freedom. The two moments m3 are acting in opposite directions, so the net force is 0. And moving on to degree of freedom 3, P3 is the applied force at the third degree of freedom. The value of the force is a moment m3. The direction is in the direction of the degree of freedom, so according to the sign convention, the sign is positive. The applied load will tend to rotate the node in the direction of the degree of freedom. So we've now obtained all the entries for our stiffness matrix and our load vector, bypassing the equations of equilibrium. Let's look at our previous result. When we went through the longer process of considering equilibrium, we found these results. For the stiffness matrix K, you can clearly see that the entries of K are arranged exactly as they're arranged on the right-hand side. For the load vector P, you can see that the entries correspond, but it's written on the left-hand side in column format instead of in row format. This finishes the topic of direct assembly. We'll be using this method from now on in solving problems.